In order to continue to develop our understanding of the models for light, we need to have a look at black body radiation, as indicated by the highlighted dot point there. The concept of black body radiation dates back to sort of the 1800s, and we're not going to go into it in as much detail as we possibly could. We're just going to have a look at some of the key factors about black body radiation. Now, the first thing is to identify what a black body actually is. So a black body is an object that absorbs all electromagnetic radiation that falls on it. When we're talking about electromagnetic radiation, we can substitute that idea of electromagnetic waves in here as well. So it doesn't just have to be radiation that we're talking about. Ultimately, though, we're interested in the energy that's falling on the object, and hence why we're using the term black body radiation. So in saying that all of the energy is being absorbed, what we're also then indicating is that no energy is reflected. So that means that all of the energy absorbed by the object, none reflected. And that's the reason why we call them black bodies. They're not necessarily actually a black object, it's just that all of that light is being absorbed, so it's not reflecting any light, and so hence the term black there. Now, real black bodies don't actually exist. There are no such things as black bodies in nature, but there are some very close approximations to it. A cavity with a hole is a good example, and black holes can also be treated as black bodies. In developing understanding of light from stars, we can also treat stars as black bodies. Now, while black bodies absorb all of the electromagnetic waves that fall on them, they will eventually re-radiate that energy at a later stage, not necessarily in the same frequency or wavelength that it was absorbed. And it was in the late 1800s where some evidence was being observed about black body radiation that started to pose a few problems, and it's based on the fact that the predictions were based on the wave model of light. It was predicted that energy would be radiated across all wavelengths of electromagnetic radiation. So an ideal black body, as it then starts to re-radiate that energy, will do so across the full electromagnetic spectrum. And as well as emitting energy across all of the wavelengths, it would also emit more energy in the shorter wavelengths. And if we're talking about short wavelengths, then that means we're really saying that it's going to be across higher frequencies. Now, to represent the prediction graphically, I'll just produce a graph under here so that we can see what the prediction was, and then we'll have a look at what the actual observation was as well. So here we have a graph of the predicted relationship, and we can see that on the horizontal axis we have the wavelength of electromagnetic radiation, and on the vertical axis we have the intensity. Now, intensity relates to both energy and power. So the higher the intensity, the more energy that's being radiated. You can see at the longer wavelengths is fairly low energy, and then as the wavelength gets shorter, the energy increases, which kind of makes sense in that if you've got something that's oscillating at a high frequency, that would tend to mean that more energy is being put into the system and therefore would be radiating more energy. Now, observations of black body radiation didn't match that prediction. And instead what it showed was that there were much lower energies at short wavelengths. So we'll have a look at what that means graphically and look at the discrepancies between the prediction and the actual observations. So this is the actual observation, or at least a representation of the relationship that was observed. So you can see on this graph that at longer wavelengths, the energy was fairly close to the predicted value. However, as the wavelength got shorter, the energy actually decreased down to 0 for shorter wavelengths. So instead of increasing up to a maximum at shorter wavelengths, there was a decrease in the energy being radiated for those short wavelengths. In further investigations of blackbody radiation, there was actually a relationship that was determined between the temperature of the blackbody and the wavelength at which it was radiating most. So we'll just make some notes about that briefly. That idea is one that helps to describe the spectrum that's going to be released by a blackbody and the peak wavelength at which it's going to radiate. So it was discovered that the wavelength at which maximum radiation occurs was related to the temperature, and that value that we'll use there is going to be lambda max. So it's not the maximum wavelength, it's the wavelength where maximum radiation occurs, and that was discovered to be inversely proportional to the temperature of the blackbody. So on the graph above, what we can indicate is the where that lambda max value occurs. So if we look at the maximum radiation, that's this point at the top of the graph, so there's the maximum intensity, and the wavelength that that corresponds to is this value down the bottom, lambda max. Now the relationship is given by Wien's law. And it's a fairly straightforward one. We've said already that it's inversely proportional. And so the equation is simply lambda max is equal to B over T. So that's the equation that's in the data booklet, linking the wavelength of maximum radiation to the temperature of the blackbody itself. And we've already identified what lambda max is. So that's the wavelength in meters. T is the temperature in degrees Kelvin. And the value of B is known as Wien's displacement constant. Now, I'm not sure why the word displacement is important here. It's just the term that's used in this relationship. And the value of that is 2.898 by 10 to the negative 3 meters Kelvin. And again, that value is given to you in the equation booklet. Now, to try and make a bit more sense of that, let's have a look at another diagram. So on this graph we have a number of different black bodies radiating at different temperatures. You can see that the shape of the curve for each of these black bodies is roughly the same. It starts off low, increases to a maximum, and then decreases back down again. So that shape is fairly consistent. What changes though is the amount of radiation that's being given off by each of the black bodies at its maximum. So you can see that each of those maxima have changed. So that's also then going to affect the value of lambda max, and just to identify where they are. So the first one would be here, the second one's a little bit higher, the third one's a little bit higher again, and the fourth one would be there somewhere. Now, with the change in temperature, the way that that works is that as the wavelength is getting shorter, so that's decreasing wavelength, as the value of lambda max gets smaller, that means the temperature is increasing. So we can see here that the peak is going to be moving to the left when temperature is increasing. So that means that the graph on the left, or with the maximum peak, will be the hottest, and the graph with the peak lower down will be the coolest. We'll have a look in more detail in class at the spectra that's emitted from black bodies and how that relates to both visible light, ultraviolet and infrared light. and we'll do that using a FET application.